Hello everyone. I'm going to do a Chapter 5 review, and it's going to be kind of a guided review where I'm going to talk through some of the key ideas, and we're going to do some practice questions from each of the sections. And then as you follow along, you should be making a review sheet that goes along with this, and then I will allow you to use that review sheet on the actual test. So this will serve a dual purpose. It'll act as a review and also as your guide when you're actually doing the test. There are 6 sections that we're going to fill in. There were 5 that we covered in the book, and one of them I split into 2 sections, so there's your 6 sections. So if you got a piece of paper, you can use the front and back, and divide it up into 3 sections on front and 3 sections on back. So here we go. The very first section, I would title it at the top 5.1. It was on finding z-scores and then calculating probabilities with z-scores. So using z-scores to get a probability. The formula that we use to find a z-score, recall, is we take a measured value, we find how far away it is from the mean, and then we divide by what one standard deviation is. All that a z-score really is how many standard deviations away you are from the average. So you subtract to find how far you are from the average, and then you divide by what one standard deviation is. That will tell you how many z-scores you are away, and the z-score is how many standard deviations away you are. Here's an example. The average score on the LSAT, which is the test that you take when you're applying to law school, so it's like the law version of the SAT, is a 151 with a standard deviation of 10. Nora took it and got a 172. What is the z-score corresponding with that actual LSAT score? Well, I would always recommend you to draw the actual normal curve. So sketching a normal curve, in the middle is going to be our average. In this case, it was a 151. And the standard deviation is 10, so this would be 161, 171. Going this way is 141, 131. We want to know what Nora's z-score was. Nora scored a 172, so right past the 171, we want to know what is the z-score for a 172. We have an idea, because really, this is a z-score of 0, because if you're at the average, you're 0 standard deviations away from the average. This is a z-score of 1. 171 is a z-score of 2. This would be a z-score of -1, -2. So we have an idea. It's going to be just slightly bigger than 2. Now we need to find exactly what it is. So the z-score is your actual value, in this case a 172 minus 151. So she scored 21 points above average. One standard deviation is 10, so if we divide 21 divided by 10, we'll see that she was 2.1 standard deviations above average. That would be, she had a z-score of 2.1. Second question asks, what percentile is Nora in? So essentially we're saying, if you have a normal curve, and you're at 2.1, the percentile is the percent that is below it. What percent of other test takers did Nora score above? Well, we can use normal CDF. So normal CDF, you put your left bound in first. This is technically going all the way to negative infinity. Well, I mean, negative infinity, so just pick a very large negative number. -1,000 is what we've been typically using, is big enough. The furthest right we go is 2.1, because we want any value all the way between negative infinity up to 2.1. Now we need to state what the average is. Because we converted to a z-score, the average is a 0, and one standard deviation is 1, since we did a standard normal, and then we type that in the calculator. So we go to here and type in second distribution, normal CDF, lower big negative number, doesn't really matter. That one's -10,000. That'll do the same as -1,000. I mean, -10 would probably have worked, but you want to be safe, so always pick a big number. We had an upper score of 2.1. Because it's a standard normal, the average is 0. One standard deviation is 1. And then we run it, and we would see that she was in the 98th percentile, so 0.982. So 0.982, so we would say about 98th percentile. That would actually be the same, so you didn't need to use a z-score there. Z-scores are really a carryover from before computers and calculators. You could have actually ran this whole thing with the original information. If you had done second distribution, normal CDF, again, -1,000. Let's use her actual score. Her actual score was a 172. The average score was a 151, and a standard deviation of 10. And if you ran it with that, it's the same thing as converting to a z-score and just using the standard normal. You'll notice you get the exact same thing. So you can either use the z-score or just the original values, but that's what 5.1 was on. 5.1 was on z-scores and then calculating probabilities with z-scores. 5.2 was on just calculating probabilities without having to first go to a z-score, and I kind of just showed a preview of that just a second ago. So 5.2 was just reiterating to you that if you know the measured value and the mean and standard deviation, if you want to find the corresponding probability, you need to use normal CDF. So we use normal CDF when we know the measured values and we want probabilities. Normal CDF returns probabilities. So continuing on, let's say Nora was debating between going to law school or going to medical school. So she took the MCAT as well. The MCAT is a test that you would take if you were going to go into medical schools. And on the MCAT, it's an entirely different scale, so that's why we might convert to z-scores first. The average score is a 25.1 with a standard deviation of 6.2. Nora took it and got a 37. Nora scored higher than what percent of other students? That's exactly the same thing as asking what percentile she scored in. So again, if you sketch the normal curve, standard deviation was 6.2 and the mean was 25.1. So I need to add 6.2, so 31.3, add 6.2. What is that going to be? 37.5. And then going down, if I start at 25.1 and then subtract 6.2, I'd be at 18.9 for one standard deviation away. Subtract 6.2, I'd be at 12.7, and you could keep going down. But that's what the curve should look like. She got a 37. So this is 37.5, so just below that. So right here. And we want to know what percent of students did she score higher than. So again, that's a percentile. What percentile was she in? We want to know what percent of students scored below here. Well, we can use normal CDF again. Normal CDF, it's a left bound of negative infinity, so just use a very large negative number. Her score was 37, so up to a 37. This time the mean was a 25.1. Standard deviation was 6.2, and then we run that. So normal CDF, negative 1,000, upper is her score of 37, average was 25.1, and standard deviation was 6.2, and her percentile, the percent of students she scored higher than, 97.3, so say about the 97th percentile. Nora is an excellent student. Last question was her LSAT or MCAT score more impressive? Well, if you look, the MCAT, she was in the 97th percentile, and the LSAT, she was in the 98th percentile, so it'd be slightly more impressive, the LSAT score. You can also see just based on z-scores. Her z-score for the LSAT was slightly above 2, and her z-score for the MCAT was slightly below 2 standard deviations, because here's 0, 1, and 2. She's slightly below 2. So you could have just told that. You could have noticed it just based on the z-score. So there's a lot of ways to say the answer here. You could say it's based on percentiles or z-scores. I'm going to use z-scores. So LSAT was more impressive since her z-score was a 2.1, and for the MCAT it was less than 2. You could also use percentiles. 90th percentile, slightly better than 97th. That's what 5.1 and 5.2 were on. 5.3 was kind of the opposite question. 5.3 was, what if you know the probability, but you want to find what the corresponding value is that would return that probability? And because this is the opposite information, you're given the opposite of what you had before, we use a function in the calculator called inverse norm. Back before calculators and computers, they just had a different table. They had like an inverse table. They would look in the table. Kind of backwards because it's the opposite. But we can use calculators and computers now, and the program that we're going to be using is inverse norm. So inverse norm is when we know the probability but want to find the value. And you'll notice that is opposite of what we just had a second ago. A second ago, we knew the value, but we wanted the probability. So example, what z-score corresponds to the 40th percentile? Well, we know it has to be below 0, so it has to be in the negatives because 0 has a 50th percentile, so it can't be here. It's got to be somewhere over here. So somewhere over here is the question, at what value do I get 0.4 below that? Well, I'm going to use inverse norm. So inverse norm. If you have the calculator sheet I passed out, has all of these functions on that little calculator sheet as well. So inverse norm, second distribution, you'll notice it's just below normal CDF. What are the things it asks? It asks for the area. So if you were showing your work on an assessment, you would have to write what you typed in. So the area that we want is going to be, we said 40th%, so 0.4. And we want z-score, so average is 0, standard deviation is 1, and we want it left of that z-score. So then we hit paste, and there we go. So what do we do? 0.4, average 0, standard deviation is 1, and then we did left. And what did that return for us? We need a z-score of negative 0.253. If we have a z-score of negative 0.253, we're going to find 40% of the values are going to be less than that. You can actually see if you run normal CDF. If you go and run normal CDF and do negative big number up to negative 0.253, you're going to find we're going to get approximately 40%. So there we go. It works just checking it backward. Now we're going to continue with that MCAT question and say this. So the MCAT, some schools set cutoff scores. Let's say again that MCAT had a average score 25.1 and a standard deviation of 6.2. Let's say a school wants to only accept the top 10%. What would the cutoff score need to be? So here we know the average is 25.1. And we want to only accept the top 10%. So there's going to be some value here. So that 10% is going to be to the right of it. That also means 90% is to the left. So you can run this in one of two ways. So we're going to do inverse norm. And what things are we going to have to input? Well, I can use this top part as a guide. If I want the top 10%, I could do 0.1. I need to give it the average, which was 25.1. Standard deviation 6.2. And if I want the top 10%, I would need to tell it right. Realize you could do this as 0.9 here and then do left, and it would return the same value. But let's just do one of them for time. So area, we want just the top 10%, so 0.1. Average, in this case, we said is 25.1. Standard deviation 6.2. And then we're going to do a right and run it. 39.5 would be that score then. So cutoff score would need to be in between a 39 and a 40. Somewhere in there they'd have to make a decision. Either accept a little more than 10% or a little less than 10%. Because I doubt you can actually score a 39.5. But I don't know, I never took the MCAT. There you go. Be aware that option for the inverse norm of choosing left and right is only if you have the most updated software on the calculator. If you don't have an option of choosing left, center, or right, I'm going to let you know that the calculator is default always to the left then. And so if you did this with a left, you'd have to change this to be, ooh, I just did that wrong. I'm sorry, that was 0.01. We wanted to run 0.1. Did I write that incorrectly? We want a top 10%. Yep, I did that incorrectly. It's not 39.5. Good thing I checked. On top 10%. So let's go run that real quick again. I did the top 1%. There we go, 33. Okay. Thought 39 was a little high for it, but 33.04. So they don't really have to make a choice. 33 would be their cutoff score then. Okay, real quick. If you have a calculator that doesn't have the option though, what you're going to have to do is know it's always set to be left, so you need to change this to be 90% or to the left. So just be aware, if you don't see an option, the default is always left, but it'll give the same value doing that. So there you go. Let's see. Okay, 5.4a was on something called the central limit theorem. The central limit theorem is how we have to adjust our standard deviation when we are talking about the distribution of averages. So instead of talking about individual values, let's say we ran multiple samples, found the average for each of the samples, and then repeated that over and over again. So we're looking at calculating probabilities not for single values, but for averages. And what happens is the standard deviation shrinks. In class, we do a lab typically where I have people look at pennies currently in circulation. Just a little thought experiment. Imagine that you were walking down the street and you found a penny and you picked it up and it had the year 1978. You think that's pretty old. That's kind of rare that I found a penny 1978. So to find an individual penny from 1978 is pretty rare, but it's not impossible, right? But what if I told you that you like found a bag of pennies and the average age or the average year for the pennies that were printed in that bag was 1978? That would be much more impressive because averages tend to be a lot more consistent. That's why you see the variability for this distribution is much smaller. And so their standard deviation shrinks. The standard deviation actually becomes the original standard deviation, and you have to divide by the square root of the sample size. So in that bag of penny one, you would divide by the square root of how many pennies were in there, and that would tell you the spread, the standard deviation of the ages that should be occurring in there. So the takeaway message for the central limit theorem is spreads for averages tend to be much, much smaller than spreads for individual values. And I would jot these little pictures down and then also write down the corresponding formulas. The mean and the standard deviation. The mean stays the same for a population and a sample. You would expect that the sample should have about the average of the general population, but the standard deviation is going to be smaller because you're dividing by the square root of the sample size. So there's the formulas. If you need to, you can pause and go back. I'm going to do an example. So here's an example. It says the scores on Mr. Smith's history final are normally distributed with a mean of 78 and a standard deviation of 11. We're going to apply the central limit theorem to find the average and the standard deviation of the sampling distribution for sample means, which is just saying the spread of all of the average scores for all of the different classes he might teach. But for his 7th period class of 35 students, state why you are justified in doing the central limit theorem and applying it. So the mean, well, if the average of all of his prior tests had been a 78, then we would expect the mean for his 7th period class to also be a 78. So the mean should not change, and that's what was set up here. We would expect that whatever the mean's been for the population, it would be that for a bunch of different samples. What would the standard deviation be though? Well, the standard deviation is going to shrink. So because it's for a sample of 35 students. The class's average should narrow down on a true value much more consistently. So the standard deviation should be the standard deviation for individual ones, which was an 11, divided by the square root of the sample size, which is 35. So 11 divided by the square root of 35 tells us 1.86, which is just saying that we would expect that for most of his classes, the average score should be no more than about 2 above and below 78, just based on consistency. Why are we justified in applying the central limit theorem? There's a little note up here. In order to apply the central limit theorem, you either need a sample size bigger than 30, or you have to be told that your population was normal from the get-go. That was not told to us. Oh, actually, it did say are normally distributed. So there's two reasons. No, it is normally distributed, and we have a big enough sample size. So we actually have both. You only need one, but we do have both. So you could say the justification is that population is normally distributed. And our sample size is greater than or equal to 30. You only need one of them. We just happen to have both. So there we go. Yeah. So what we're really saying is for his individual students, his individual students tend to score 78, and have a standard deviation of 11, so 89 and then 100, and then did I say 78 right? Is that right? Yep, and then going 11 below, 67, 56, right? But his average scores, right, should be around the average score for his students, around a 78, but they're much more consistent. The average score is going to be a lot narrower than the average score for individual students. This is the average scores for classes. They're much more consistent. So 1.86, so this would be like 80, and this would be like 76. So this is for like individual students, this is for class, and that's what the central limit theorem is trying to get to. Averages are much more consistent, less variability. Now we're going to apply that in 5.4. This should say B, 5.4b, second section. Same information, just now we're applying it with probabilities. So Mr. Smith's class again. Now, what's the likelihood a single student in his class scores a 90 or higher? If it's a single student, I'm going to be using the typical population distribution where the mean is the mean and the standard deviation was given to us. So for a typical student, you can see, right, 78 and then 90. So 90 would be like somewhere here. So not impossible, can happen. There's going to be a decent amount of students that might do that. So I would use normal CDF for this. So my mean is 78, my standard deviation is 11, and then I use normal CDF. Normal CDF. My left bound is the score of 90. I want 90 or higher. So technically the highest value is 100. You could set it to be 100. I'm just going to do 1,000 just to be consistent. Both would be the correct approximations. The average score is 78, standard deviation is 11, and then I just run that. So normal CDF, I want 90 or higher, big number. Average scores is 78, standard deviation 11, and the likelihood that an individual student scores a 90 or higher is like 13.7%, 13.8. Okay, so it can happen. What's the likelihood, though, that his entire 7th period class of 35 students has an average score of 90 or higher? You should have like some red lights going off right now. It should be highly unlikely the whole class has an average of 90 or higher. I mean, look at the distribution here for the average, right? One standard deviation is 2. You are like 6 standard deviations away from average if you were to have a whole class have an average of 90. So it's like all the way over here. This is going to be impossibly small. If that occurred, he would have some clue that there probably was some cheating going on. So let's actually see what the probability is that would give him some justification. The average, again, should be a 78. If students are scoring a 78, then an entire class should have an average of about a 78, but the standard deviation is going to be much smaller. It's going to be the standard deviation for an individual student, which would be 11, divided by the square root of the sample size, so 35. And we did that a second ago. It was this guy, right? 1.86. Okay, now I'm going to find the probability. Normal, CDF. I want the average to be 90 or higher, so 90 up to technically 100, but let's just say 1,000, or just pick a big number. 10,000 is definitely big enough. Average is 78, but now your standard deviation is much smaller. It is 1.86 because we're talking about the distribution for averages. So I run almost the exact same calculation. The only difference is I need to change the standard deviation to be 1.86, and my probability is going to be very small. That is essentially 5.5, so that's like 6, if I round to the nearest integer. 6, this is times 10 to the negative 11th. So this is essentially, we'll do it, 5.5 times 10 to the negative 11. If you wrote this out, that's times 10 to the negative 11. Scientific notation, you divide by 10 11 times. It would take you once to get past the 5. There'd be 10 zeros. So decimal, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 5. That is how unlikely it would be to have an entire class having an average of 90 or higher based on the information. And that's what the central limit theorem tries to get the point across. Averages, if you do distributions for averages, they are a lot more consistent, less variable. So if you get value is far from average, it's unlikely. Last part is using a normal approximation for binomial situations. We knew from the last chapter that a binomial situation has an average that is equal to n times p, where n is the number of trials that we're running and p is the probability of success. That hasn't changed. The standard deviation, we did this last chapter, is equal to the square root of n times p times q. In order for us to be valid in approximating the normal to the binomial, you need n times p to be greater than or equal to 5 and n times q to be greater than or equal to 5. This kind of comes from the idea that unusual is less than 5%, and we'd want things that are not going to be terribly unusual. This kind of has to deal with some skewness too, so that's where that comes from. But you need to check that n times p and n times q are both at least 5 in order to approximate a binomial with a normal. So here's an example. It says it is estimated that 10% of people are left-handed. Use a normal approximation to estimate the likelihood a group of 100 people has 15 or more left-handed people. So let's find what the average and the standard deviation should be. N is 100 in our trials. P is the probability of success. Being left-handed is 10%, which means failure being right-handed is 90%. The average number of people in a group of 100, you could do this in your head, would be 100 times 0.1. We'd expect about 10 people to be left-handed. What should the variation be in the group? The standard deviation would be 100 times 0.1 times 0.9. I believe that turned out to be 3. Let me check it real quick. 100 times 0.1 times 0.9. That is 3, which means if you drew the normal curve that we have going on here, we have an average of 10 and a standard deviation of about 3. So over here would be 13. We want 15. So let me back this up just a little bit. 13 and then maybe like 15 right here. This is kind of the situation we have going on. Okay, now I'm going to use a normal approximation for this because I want the likelihood that 15 or more people in the group are left-handed. Here's the problem. We are approximating something that is discrete. You could not have in the group, 10.8 people being left-handed. So the problem is binomial distributions are inherently discrete. So when you draw these, items in, here's 10, here would be like 11, and then 12. You kind of get the idea. I'm not going to draw them in. It kind of makes the picture messy. But they're individual bars because these are individual people, measurements that could occur. I want 15 or more. Now, in order for me to capture all of 15, I actually need to notice that 15 is 1 wide. If it is 1 wide, it actually means it goes between 14.5 and 15.5. If I want to get 15 or more people, in terms of the normal, I need to actually get all of 15, which is going to be 14.5 or larger. And this is what we call the continuity correction. If I want to get all of 15, I need to do 14.5 or larger, and then I can do a normal. So normal CDF, my lowest value, if I want to get all of 15, which I do because it said 15 or more, 14.5 all the way up to technically 100. You could just pick a big number. Why 100? Because I said there was 100 people in here, so the most amount you could get to is 100, but 1,000's fine. Approximating anyway, it'll be big enough. Average is 10, standard deviation is 3, and then I run it. So normal CDF. Oh, I did inverse norm. I don't want that. Normal, don't do that. It's in function inside a function. Normal CDF, lowest we said is 14.5 because that continuity correction. Upper, pick a big number. Average is 10, standard deviation is 3. What's the likelihood we get 15 or more left-handed people? About 6.6, about 7%. So 0.067 if you rounded. So there you go. And that should cover the chapter. I hope this helped. Thank you very much. Have a good one.